Great, and we're back. Welcome to Unit 2, which will hopefully be on variable material. All right, so element of the day is radium. There are many radioactive elements, but radium is more famous than most of them. This is the element that used to be painted onto glow-in-the-dark watch hands. It doesn't glow because of radioactivity. It glows because it absorbs light energy and then re-radiates it in a color that we can see, specifically a kind of a yellowish color. Unfortunately, the people that used to paint these wash hands by hand were told to lick their brushes to keep them sharp. And most, if not all, of the long-term workers painting the watches got cancer of the mouth. Now, this was something that the company that was making the watches was fully aware of, but they kept on doing it. So I guess beware science and beware capitalism as well. Up to you, of course. Unit 2, we're going to do patterns in the night sky and constellations in this recording. After that, we're going to do another recording for seasons, and then we'll do a recording for phases of the moon / eclipses. So in this unit, in this recording, we'll do motions in the night sky, constellations, meteor showers. And I'd like to start just by showing you all a great picture. And here it is. This is something called the California Nebula. It is indeed reddish. If you're in truly dark sky, you can see the reddishness of the nebula. And that's on the left-hand side. Towards the center is my favorite grouping of stars, the Pleiades, which is a group of a ton of stars. They're just now being born. Well, actually, I should say they were born a while ago, since the light has traveled towards us for quite a few years. You only see the bluish stars because only the bluish stars are bright enough to be visible here. Luminous enough, I should say. But in fact, that star cluster is full of stars of all different colors. And I showed you this picture to highlight two things. Thing number one is that the sky used to be much richer to our ancestors than it was to us, because our view of the night sky is completely washed out by lights from cities. And so in a very real way, humans have to some extent lost touch with what is really up there in the sky. Astronomy has been going on for a while. We've touched on this. Top left, you see Stonehenge, which is the most famous of the rock rings that were used to keep track of the seasons. We're not sure what all Stonehenge was used for besides that, but it was definitely used to keep track of the seasons. These sorts of rock circles were also extremely common in the area around the Mediterranean Sea. We found them all over the place, including in Egypt. Stonehenge just happens to be the biggest. There is a Iranian astrolabe top right. Notice that most of the famous stars have names in Arabic. Aldebaran, not an English word, for example. That's because it was really Muslim culture that carried astronomy forward after Europe's culture and civilization collapsed in the fall of the Roman Empire. Bottom left is a Mayan observatory, El Caracol, and the Mayans had many observatories. It is hard to say what they used them all for, because when the conquistadors arrived in South America and Central America, they burned all the books. They faced all of the writing. And, about 50 years after that, clerics came and tried to reconstruct what was known of those civilizations, but it was too late. The information had been lost. And then bottom right is ancient Beijing, and Chinese astronomers were extraordinarily good at what they did, and have been throughout all of China's cultural history. And we have extremely good records about that because China's culture never really lost track of its written record of history. So here's the Milky Way. You only see it in summer in the northern hemisphere and winter in the southern hemisphere. So, question for you. What month is it here in the northern hemisphere when it is winter in the southern hemisphere? Take a moment, pause the video, ideally chat with somebody on GChat, and then come up with your answer on pause, and I will tell you. In about June, it is summer in the southern hemisphere, and in about June it is summer in the northern hemisphere, and in June it is winter in the southern hemisphere. The two hemispheres have flipped seasons. When it is spring in the northern hemisphere, it is fall in the southern hemisphere, summer in the northern hemisphere, winter in the southern hemisphere, autumn in the northern hemisphere, spring in the southern hemisphere, so on and so forth. More about that when we study seasons. So remember, it is the Earth that is moving, not really the stars on the time scale of a human day. And so this YouTube video may help you visualize what is going on with the night sky, but if you're prone to vertigo, get ready to hit the pause button in case you start to feel ill, which can happen. This is a bit of a disturbing video in some ways. So everybody's known the Earth is round for forever. Like, this is something that pretty much every culture on the planet figured out around the same time that they developed more sophisticated tools like wheels. So most people knew, but what was not known is that the Earth spins. The ancient Greeks believed the Earth was a stationary sphere surrounded by a rotating sphere of stars called the celestial sphere. The sun, moon, and planets would all have their own separate sphere, which would rotate separately. Now let's go up to the board. So why? Why did the ancients think that the Earth was not spinning? Well, this is kind of a modern invention, but we certainly had analogs to it back in the day. And back in the day, we also had people that are much better at drawing than me. Oops. So this is a carousel, unless it's a merry-go-round. I'm not sure which is which, but this is the sort that you see in a playground. And a kid or an adult can grab onto the outside and run with it. It starts to speed up and speed up and speed up. If you are a person over here, you feel what appears to be a strong force pushing you outwards. That force is not real. It's just a consequence of your body trying to go the same direction as it was going and being forced to travel in a circle. But nonetheless, it sure feels like a force. And then in the middle, you don't really feel any force at all. You don't have to hang on one bit. You still get tremendous vertigo, but you don't have to exert any effort to hang out there. So why might one think that the Earth is not spinning? Well, if it was spinning, wouldn't there be an enormous force on the outside that would make you fly off? Because if it was spinning, it would be spinning very fast in order to encompass one full rotation every day. So it seems natural that the Earth would be stationary. And also, what would the world look like if the sun did go around the Earth? It would look just the same. Sun comes up, sun goes down. There's no immediate give that indicates that the Earth itself is the rotating object. So when the ancients say the celestial sphere, they mean that they're going to imagine that the sky itself is turning around the Earth and all the stars are fixed on the sky somewhere very far away. And that is not the accurate view of what's going on. What is actually happening is that the stars are more or less stationary and the Earth is turning. But nonetheless, the idea of the celestial sphere can be extremely useful in terms of visualizing what is going on with the sky. We call a recognizable pattern of stars a constellation, and it means a little bit more than that. It's also something that has been recognized by the International Astronomical Union. So not every recognizable pattern of stars is a constellation, but this is one. There's Orion. Now, what constellations look like is a coincidence of where the Earth is. If you were to circle around Orion at much faster than the speed of light, you can see that what we call constellations is a blend of extremely luminous stars that are pretty far away and fairly dim stars that are fairly close. So if you were to be in an entirely different part of the galaxy, the constellation we know as Orion would look extremely different. Now you'd have to go a fair distance to actually get Orion to look different. If you were to hop over to the nearest star from us, Proxima Centauri, Orion would look basically identical. So you need to move by quite a bit before the constellations start to form like this. Go ahead and play the video, it's fun. So back to the celestial sphere, it is useful. So here you are standing on the Earth. The point directly above you is called your zenith. Your horizon represents everything you can see when you look out all around you, just rotating in one big circle. And then the north celestial pole and the south celestial pole are fixed points on the celestial sphere about which the stars rotate. So stars around the north celestial pole are rotating clockwise, and stars around the south celestial pole are rotating clockwise. Something that I always had difficulty with, but nonetheless, it is still true that things rise in the east and set in the west. It is a function of perspective that some of the stars are going clockwise and some of the stars are going counterclockwise. They are all indeed going the same direction. So here's another way to visualize your zenith and the horizon. The zenith is the spot right ahead, which is definitely not necessarily the north or south celestial pole. For example, over here, you're standing in kind of about Napa, your zenith is directly overhead. If you point up, you're not pointing towards the north celestial pole at all. You would need to point sideways to be pointing towards that. And if you can find the north celestial pole, you have found the exact direction that north is, and you can use that to guide yourself. So imagine you were standing at the North Pole, looking directly at your zenith and watching the movement of the stars. I want you to pause and draw a picture of what this motion looks like from your point of view, and make sure to indicate the direction of the motion that you see. So remember, you're moving your body from where you're standing now in this picture all the way to the North Pole. And so your perspective is going to shift over to that perspective of being at the North Celestial Pole. So do the drawing, then unpause, and this is what it would look like. The stars will be moving counterclockwise around the North Celestial Pole. And currently there's actually a star in the middle of the North Celestial Pole. If you can find that star, you always know exactly which way north is. Now imagine you're standing at the North Pole, but you look directly at your horizon. What would the motion of the stars look like from your point of view there? So now here you are, you're standing at the North Pole, things are going around in a circular fashion, and your horizon would be basically the same horizon as you would have at the equator. Not that you can see everything that you would see at the equator, but it would be flat relative to the equator. And that would look like stars just streaming over more or less horizontally. Now imagine you're standing on top of this building. You're facing north and you're watching the movement of the stars. So Napa's at about 37-ish degrees north, 122-ish degrees west. Draw a picture of what this motion would look like from your point of view. So when you're over here, standing approximately in Napa, looking at the North Celestial Pole, what would you expect to see? It would look like this. The North Celestial Pole would be about 37-ish degrees north above the ground. And so not only does the North Celestial Pole tell you which way is north, but it also tells you how far away you are from the North Celestial Pole. As soon as you can see this central star, you know basically how close you are to the equator, or how close you are in between the equator and the North Pole. 37 degrees north means you are, by the Earth into 0 to 90 degrees going from the equator to the North Pole, means you're 37 degrees away from the North Celestial Pole. By the time you reach the equator, the North Celestial Pole would be dead on the horizon. So what will the sky look like at 30 degrees north? Well, now you would see the North Celestial Pole 30 degrees above you, and you would see a lot of stars, and those stars would largely rise and set every day. There would be a set of stars very close to the North Celestial Pole that would always be up, but you would not always be able to see them because this thing happens called daytime. And so they'd often be washed out by the sun. So there's another image of what it looked like. North Celestial Pole, the star at the North Celestial Pole would be dead on 30 degrees above the horizon. Here's some real life pictures of star trails. You can do this with your cell phone camera if you just set it to being on a very long exposure. The key thing is you need to get an extraordinarily stable tripod. Your camera has to remain absolutely still to capture this kind of image. So this star trail is taken pretty close to the equator. The North Celestial Pole is fairly low. Here is what the star trails look like up around San Francisco. More star trails, one on the left. In Canada, one on the right, much closer to the equator in Utah. And then what would the sky look like at the equator? Well, now the North Celestial Pole and the South Celestial Pole will be dead on your horizon. Every single star that could be seen on Earth is in theory visible as long as you wait for a time of year that the sun is not washing it out. And there are no stars that are always up. The fancy word for stars that are always up would be circumpolar. They circle the poles and they never set. But that is not true at the equator. So North Celestial Pole, dead on the horizon. South Celestial Pole, dead on the horizon. Here are the things that actually count as constellations, as defined by the International Astronomical Union. The big famous ones are the constellations of the zodiac. And those are the ones that the sun physically travels through. So you've got Aries, Taurus, Gemini, Cancer, so on and so forth. If you look towards the north and to the south, things get to be pretty distorted. And the reason that they're distorted is that this map is a Mercadian projection. It's a flat map of something that's actually a sphere. And so same thing is true with Earth. When you do this kind of thing, you highly exaggerate the top and the bottom. For example, by looking at a normal map, a normal flat map, one can get a very strong sense that Greenland is the same size as Africa. But as a matter of fact, Africa is huge, huge, huge in comparison to Greenland. But things get so distorted by projecting a round thing onto a flat surface that you've got to distort something. And traditionally, we distort things near the poles rather than distorting the middle. Okay. Now that you're not looking at that map, of course you've got the PowerPoint slides open in front of you, so you could always click back. But go ahead and write down every constellation name you can think of. Then write down every star name you can think of. Go ahead and pause. Just go through it in your head. Think about how much of the nomenclature of stuff in the night sky you already know. And then let's go back to it. So Ursa Major, Ursa Minor, Perseus, and all the zodiac signs are all the ones I know. And I teach astronomy. One more thing to draw your attention to. Towards the north, these constellations largely have names that are drawn from either Europe or the Arabic world. Towards the south, the names get to be quite a bit stranger. We've got a constellation, Puppis, which I assume is for puppy. We've got a constellation, Telescopium, for telescope, Microscopium, from microscope, Chameleon. So the constellations of the northern hemisphere were named by people that live in the northern hemisphere. Constellations in the southern hemisphere, also named by people that largely live in the northern hemisphere. Two reasons for this, I guess. One of them is that there's just a lot more people in the northern hemisphere. So check out the amount of land up here in comparison to the amount of land down here. Second, and probably the more meaningful reason, is that colonization happened here, and here, and here, here, here. Yep, that's about it. Well, India as well, and swaths of China. And so in the areas where colonization happened, largely the local cultures got wiped out. And so nobody was asking them what their names for the stars were. Certainly not the International Astronomical Union. All right, so the celestial sphere is in theory simple, but in reality, it is a hard thing to wrap your head around. I would like you to use this link and fast forward through several months and a few days to see how it changes. So play around with it. What star is it that's here? Pause, think about it, watch my explanation. Okay, so first off, what star is this? The answer is the sun. If you go all the way to the North Pole, during summer at the North Pole, the sun just circles around and around and around, just like any other star, and for the exact same reason. And then jumping ahead to the topic of seasons, if you go into winter at the North Pole, then the sun never rises at any point until you get back. Excuse me, I'm using a touchpad here. Does not work great. Until you get back to the sun. At the South Pole, this is completely reversed. The sun is perpetually up at the North Pole. At the same time, the sun is perpetually down at the South Pole. And then in the equator, which I guess I will get using keyboard commands, the sun is traveling more or less directly overhead, but it does have some variance. Now it's completely overhead, perfectly overhead, rising due east, setting due west. And it goes a little south of the equator, goes back north. Now it is again directly overhead, rising to the east, setting to the west. And then it goes a little north of the equator. And that is my exploration of this applet. But I hope that you try several different spots and play around with it more yourself. Okay, so let's figure out what stars look like from the southern hemisphere, from the equator, and how that differs if you're facing north or south. Open up NAAP Labs, that's virtual to download. Click on Rotating Sky, and then click on Rotating Sky Explorer. So hopefully you're getting this up at the same time. I am learning that I have way too many programs open. So give me a second to find it, since I foolishly opened every single applet I'm going to use in this diagram. So you can have star patterns, both known ones and random ones. There's a Southern Cross. That's what you use to find true south in the southern hemisphere. I will take it away real quick just so you can see what it is. There it goes. Southern Cross, not visible from most of the northern hemisphere. Oh. So, no stars at all. Let's just start adding stars randomly. And then let's go right up to the North Pole. Sure enough, you look straight up, the stars are going round and around and around. Let's go all the way, and then if you look sideways, they're just moving more or less parallel to the horizon. All the way to the South Pole. Opposite direction, but same basic thing. And then at the equator. The North Celestial Pole is dead on the horizon, the South Celestial Pole is dead on the horizon. And you should be able to see every star in the sky, provided you're willing to wait a year so that the sun isn't up, washing out some of the stars at certain times. And then you can go and see exactly what the stars are like at Napa, should you care to. North Celestial Pole a little bit above the horizon, South Celestial Pole completely hidden. A bunch of circumpolar stars that never set, Also a bunch of stars that do set. So that's where we are right now. Or so I assume in this era of Zoom. One never knows. So play around with this as much as you possibly can because it will really help you understand. Okay, so which of the following images could have been taken at the equator? Go ahead, pause, think it through, give me an answer. I think that image B, which has somehow become unlabeled, that's the one that's in the middle on the left, could theoretically have to be taken at the equator. And image A at top left could theoretically be taken at the equator. Because there's clearly a celestial pole, be it north or south, right on the horizon at A. And then on B, the stars are rising straight as you look at the horizon, and then they are more and more curved as you look to the right and to the left. And of course, one way it's going counterclockwise, the other way it's going clockwise. But one way or another, they are still rising in the east and setting in the west. So, a quick puzzle for you. How do you find the direction north? And this only works from the North Pole to the equator. I've given you the answer several times, but here's a fun riddle to go along with it. Where on Earth can you go 12 feet south, 12 feet east, and then 12 feet north and end up back where you started from? The answer would be the North Pole, and there's a star currently hovering right above the zenith of the North Pole, and that star is called Polaris. And Polaris is the star you look for if you want to know which way north is. And you're in the northern hemisphere. So the Big Dipper is pretty visible. Little Dipper is a lot harder to see, and Polaris is the last star in the candle of the Little Dipper. Keep in mind that the whole sky is circling around Polaris in the northern hemisphere, and so the Big Dipper need not necessarily be to the bottom of it. It could also be the top. So the constellation of the Little Dipper, the constellation the Little Dipper with Polaris in it is always up at night because it's very close to the North Celestial Pole in the northern hemisphere. You got to get almost all the way to the equator to have any part of the Little Dipper be obscured at all. This is not true of the constellation Ursa Major that the Big Dipper is in. So sometimes the Big Dipper is below the horizon, and there's nothing to point to Polaris. Polaris is pretty far away to be a bright star in the night sky. Amusingly, Polaris is a variable star. It grows bigger and smaller and bigger and smaller, and also grows brighter and dimmer and brighter and dimmer. So when Shakespeare writes for Julius Caesar, I am as constant as the northern star, that's not saying much if you're thinking about it in terms of size and brightness. So in theory, the way that you find Polaris is you find the Big Dipper, you measure the distance in between the two stars at the end of the Big Dipper, and then you go out about 6 more times than the length of that, and you should be looking right at Polaris. But again, hard to see, particularly hard to see in a city. So how does Polaris move? Once again, open up NAAP Labs, click on Rotating Site Explorer, and then on Sidereal Time and Hour. You can use the sidereal time to change what time it is. You can change where the star is using right ascension and declination, or just by flat out dragging the star around on it. Oh, so let's take a look at this. Excuse me, my computer chunks through and actually lets me find this program. And there it is. So Polaris is just hanging out there, not moving. I've got this random star that is visible from where this person's standing. If I want the star to be at Polaris, I've got to physically drag it over there. So I'm doing a terrible job of, there we go. Still not quite there. So where is this person? They are more or less at the equator. The latitude is 15 degrees. If I put them up more and more and more towards the North Pole, the star is more and more overhead, but still not exactly at Polaris. There we go. And then if I take him or her all the way to the South Pole, then Polaris will not be visible at all. And again, there is not currently a star at the South Celestial Pole, so it's a lot harder to figure out which way is true south. So there's a word for things that aren't constellations. The Big Dipper, the Little Dipper aren't technically constellations, as defined by the International Astronomical Union, even though they're amongst the most recognizable objects in the lunar sky. We call objects like this asterisms, which is a name for a portion of a constellation or of a few different constellations combined. Example would be the Summer Triangle, which has a star. Each of the stars in the tips of the triangle is in 3 different constellations, but it's very easy to pick out in the summer, far easier than a normal constellation. All right, so the Earth is precessing. Just as the axis of a rapidly spinning top wobbles slowly in a circle, so too does the axis of the Earth wobble in a 26,000-year cycle. Today, the North Celestial Pole is near a star called Polaris. About 5,000 years ago, it was near close to a star called Thuban, an Egyptian word because Egyptians were the people who first identified this as being the current northern star. 14,000 years later, it'll be close to the star Vega. And then if you wait a full 26,000 years, it'll be Polaris again. So I'd like you to watch this video. Feel free to skip around it, but this is a physical object evidencing the motion. Of course, this top has friction doing work on it and increasing the wobble. Earth basically doesn't experience friction because, and plus our moon keeps us very, very stable. Note that this is why the zodiac is changing, because by this point the zodiac is several hundred years old. It is currently off by about a month. In 24,000 years, the zodiac will be back in sync with the time when it was actually created. So your zodiac sign means what sign was blocked by the sun at the time you were born. So if you're, for example, a Gemini, that doesn't mean that you can go outside and Gemini is high on your birthday. It means that Gemini is clear on the other side of the sun on your birthday. So you actually have to wait for a while to see the constellation that you were born under, because you weren't born under it. You were born with that constellation on the other side of the solar system. Okay. If you're curious what your current sidereal, which means with respect to the star's zodiac is this. Look under sidereal date. So like I said, it's slipping. Which constellation is blocked by the sun is changing because the Earth itself is precessing in a great circle. Now, when I say that it's precessing in a circle, I don't mean that it is ever going to be straight up and down. The Earth is always going to have about this inclination relative to the rest of the solar system. It goes around in a circle, just like every other planet. Every planet moves in pretty much a flat plane, and they all pretty much move in the same flat plane. What it does mean is that the Earth's, which direction the Earth's North Pole is in, is pointing towards, and which direction the Earth's South Pole is pointing towards, will slowly change as the Earth goes like this over the course of 26,000 years. So this does not happen fast. It does happen fast enough that a large number of cultures caught on to the fact that it was happening well before the rise of computers, but it is a very slow effect on the scale of human lifetimes. So I think I just did 52,000 years because I went around twice. Long time to wait. And the reason that this rotation of the Earth has an effect on the zodiac is that the precession of the Earth affects when the seasons happen. And we want July to stay warm in the northern hemisphere. We want July to stay cold in the southern hemisphere. Because of that, we just physically take the calendar and alter it. Like we change the months every few years, mainly by the introduction of leap days. And when we are changing the months in that fashion, we are taking the Earth out of alignment with the stars in comparison to where it was when the zodiac was invented. So because the Earth orbits the sun, different constellations are visible at different times of the year because the sun absolutely washes out the constellations when they're on the far side of it relative to Earth. And so right now in September, constellation Leo is blocked by this, well, it's not September now, but if you're born in September, the constellation Leo is the constellation that's blocked by the sun. If you're born in November, the constellation Scorpius blocked by the sun. Born in October, there's a toss-up in between Virgo and Libra. And the apparent path that the sun takes across the sky over the course of an entire year is called the ecliptic. The idea of ecliptic is super important because it's not just the line that the sun takes across the sky, it's also the line that every single planet takes across the sky. So if you watch the sun rise, keep rough track of where it goes across the sky, and then watch the sun set, if you look at that exact same path, that's where every single planet is going to be making its journey. So this model of the solar system is not what we currently believe to be the correct one, but you can learn from it. If you'd like to see the current model, it's also under NAAP Labs. So let's start by opening solar system models and then the Ptolemaic simulator. Pause the video, watch the simulator for a while to see a planet doing something unexpected before you listen and watch me use it. We'll talk about this behavior in Unit 3. Oh, wait, sorry. I just reopened this, and I'm in fact going to the Ptolemaic simulator. So let me get there. Here we are. So again, this is not what we think is happening with the current scientific understanding. But this model is created by assuming the Earth is center of the solar system, everything else moves around it. So the red dot is Mars. Mars is moving around. And the odd thing just happened. Let's wait for it to happen again. Look at the bottom of the screen. Mars moved backwards against the background stars. Well, might you wonder, what does a planet inside Earth's orbit do? So here's Venus. Does the exact same thing. These are called epicycles, and they will be a big topic in Unit 3. The thing that's relevant to Unit 2 is look at the sun going through the zodiac. So this person was born a Sagittarius. Somebody born here would be born an Aries. Somebody born here would be born a Leo, so on and so forth. Your zodiac sign is the sign that is blocked by the sun when you were born. So once again, back to NAAPX, open Motions of the Sun, then Motions of the Sun simulator. Please play around with it before you watch my explanation on this. So we've been here before. I just want to make sure everybody understands. Here we are in the summer at the North Pole. Here we are in the winter at the North Pole. Sun never rises. Sun never sets. Fast forward a few months, situations reverse. And all stars follow the same rough path as the sun. They all rise in the east, set in the west. So here's the sun, rising in the east, and then setting in the west. So, as I said, depending upon what time of year it is, there are certain constellations you just can't see. In June, you can't see Orion at all. It's blocked by the sun. But in December, Orion is very visible. That's why Orion is a wintertime constellation to people living in the northern hemisphere. In March, you can see Virgo, great. But in September, you can't at all. In September, you can see Pisces. And in June, you can see Opus Helios, which is a new invented constellation that the IAU stuck in the middle of the zodiac for whatever reason. So now we're going to do some astronomy ranking tests. Remember, I'm not going to upload the answers. So it would be to your advantage to take notes in case I were to take some of these and use them in the quiz. Okay, exercise 1. You can see both the sun and the other stars during the day. This is what the sky would look like looking south at noon on January 1st for an observer in the northern hemisphere. The sun would appear in the sky next to the more distant stars, also showing the constellations that would be visible above the horizon at this time facing south. Starting with how the sky would appear at sunrise, rank the order that the sun will appear next to each constellation, if at all, over the next several hours until sunset. For simplicity, refer to the constellations by their letter rather than the actual name. Pause. Figure out what your answer is. Unpause. The sun is going to stay in Sagittarius over the course of an entire day. It will eventually leave Sagittarius because it is pretty close, but it's going to take about a month, which is about the length of a zodiac sign, right? So hang on while I attempt to draw 12 different assortments of dots. One, two, three, four, 5, 6, 7, 8, 9, 10, 11. I'll just take 12 here. Okay. So let's say this is Sagittarius. And so the sun is in Sagittarius. That means it's blocking Sagittarius. And here's the Earth. So over the course of a single day, the Earth spins once. So stars rise, stars fall. The sun is blocking Sagittarius the entire time Earth spins. If you want the sun to be blocking something else, you've got to wait about 1 month. Now there's a different constellation blocked by the sun. I have no idea what constellation comes after Sagittarius because I'm not all that into astrology, but it would be a different one. All right, so for this one, the sun is constantly next to Sagittarius unless you're willing to wait days and days and days. Exercise 2. Exact same setup. Imagine that you can see all these stars during the day. This is what the sky would look like at noon on January 1st for an observer in the Northern Hemisphere. So there's 5 constellations labeled A through E. I would like you to rank the constellations in the order that they would first appear to rise above the horizon on this day. So things rise in the east, set in the west, rewind time 12 hours so that all these constellations are beneath your horizon. And then imagine they start to rise, which is first, which is last, what are the ones in the middle? Pause, unpause, Libra rises first, then Scorpius, then Sagittarius, and with Sagittarius, the sun comes up, so you can't see Scorpius or Libra anymore. Then Capricornus rises, still can't see that, sun's up, then Aquarius would rise. Now, some stars around the North Pole. So there's Polaris, labeled the North Star. And I would like you to first draw this and draw a short arrow to indicate the direction that each star will appear to move. Things rise in the east and set in the west, so that'll help you. And then rank the stars in the order that the stars first appear in the eastern part of the observer's sky for the day shown. While you're working on that, I'm going to redraw the picture poorly. Once again, my apologies for my art, such as it is. Here is the North Pole with Polaris at it. There is star D. This circle is dipping beneath the horizon, and with it are stars B and C. And then over here, we've got a much bigger circle that's spending a lot of time beneath the horizon. And that is lucky enough to hold star A. A should not be that close to B. All right. That is lucky enough to hold star A. So which rises first? Well, I would say D rises first because it never sets. So D is constantly up. Let's just say that it wins the rising first contest. And then the order in which stars rise requires you to imagine that the sky is turning like a record player, which it very much is. So all of the points along these lines are fixed. So star B will rise next, then star A, then star C. And if there were to be a star here, that would rise at the exact same time as C. If there, well, okay, if it were to be there, that would be circumpolar. Never mind, forget I said it. But anyway, earliest D, then B, then C, excuse me, then A, because A rises here, then C. Any questions? Shoot me an email or get on Zoom after you schedule a Zoom meeting with me. Some of these are very likely to be recycled because it's easy to just grab the image and write multiple choice questions for it. So worth understanding. Okay, so now we're ranking the constellations from when they're highest in the sky to furthest below the horizon 6 hours after the time shown. 24 hours in a day, so 6 hours is 1/4 of a turn of the sky. If you take this and you turn it, so stars are setting to the west, then Aquarius is going to be dead up. So that's highest. Then Capricornus will be next lowest. Sagittarius will be at the horizon and the sun will be setting. Scorpius will be below the horizon, and Libra will be well below the horizon. And for this, it's the same old picture, but you need to draw a short arrow to indicate the directions each star travels, and also rank the stars in order of the number of hours that each star is above the horizon. Now I am very much regretting erasing the last image. Here we go again. D. C, B, and then on this truly large circle, we got A. So the key way to figure out how much time a star spends above the horizon is to consider how much of its circle is below the horizon. A little bit of this star's circle is below the horizon. A lot in comparison to this star's circle is below the horizon. And star B's circle is always above the horizon. So I would say that D is up for the longest. And then these two are on the same circle, so they're going to be beneath the horizon when they're here, and that's going to take the same amount of time for both of them. They aren't up at the same time, but that's not what the question is. The question is, how many hours are they up, ranked in order of greatest to least? So B equals C, and then finally the one of these that's above the horizon the least at this spot on Earth is A. It's still up a lot, but it's spending less time above the horizon than the other stars. Okay. I do not think that was the last one. Oh, it was. My apologies. So there were your ranking tasks for motions of the stars. And if you were having trouble with them, shoot me an email, ask for a Zoom meeting, let's fix it. And then finally, just because I didn't know where else to put it, we have meteor showers. So meteor showers seem to come from one spot in the sky, and that spot is called a radiant. The tracks of the meteors diverge from a point in the distance, just as long parallel railroad tracks appear to do. It's almost always more efficient to watch meteor storms after midnight, after local midnight, than before midnight. Why do you see so many meteors after midnight? Well, picture the Earth sailing through a debris field left behind from a comet, which is basically what a meteor shower usually is. For the most optimal approach to encounter them, you want to be turning into the debris field or away from it. So let's say we're going through some comet junk. We're plowing through it. It's sitting more or less stationary in comparison to the Earth, but here we are going towards it. as we go towards it, I'm gonna have to get rid of this, so I'll draw some common stuff up on the board. And I'll also remember to turn on the Blackboard video. So there it is, a bunch of leftover comet debris. And I'm going to show you the Earth from the North Pole perspective. So here the Earth is getting closer and closer and closer. If you are, oh, I've got to rotate the wrong way. My apologies. If you are after local midnight, then you are turning into the debris field. Before local midnight, you're turning out of the debris field. Let me just make sure, because I do get flustered the closer I get to a board. The Earth is definitely turning this way. So as we sail through, we need the sun to be over there, or else we don't see anything at all. So sun that way. A meteorite shower happens while the sun's up and nobody cares because nobody can see it. And so this is midnight, directly opposite the sun. After midnight, turning into the debris field. Before midnight, turning out. I'm still going the wrong way. This is clockwise. It's going counterclockwise from this point of view. I'm so sorry. When you hover above the North Pole of the Earth and look down, the Earth is going counterclockwise. This is correct. Not what I did before, which may also be correct. I just can't remember, and I probably did it wrong because I'm close to a chalkboard. That tends to be when I do things wrong. Back to the slides. So meteorite showers are generally named after where the radiant is in terms of constellations. For example, the Leonian meteor storm is so called because the radiant is in the constellation Leo. And they tend to be better the more recently the comet has passed by. Every time the Earth sweeps through the comet field, we get more and more and more of the debris. And so the meteor showers get to be less and less and less impressive. I've already said all of that, but feel free to pause and read it. Here's a Perseid meteor shower, so named because it comes from the radiant appears to be in the constellation Perseus. Now, these aren't always ice chunks. Sometimes some pretty big chunks of metal fall to Earth in a meteor shower. So here's a 15-ton meteor that was found, which probably made quite a dent when it plowed into the Earth. But it did that a long time ago, so we don't know for sure. And here's a more modern take on meteorite watching. Check out 3 minutes, check out 7.5 minutes, come back. So you're back. I just wanted to say that this did not kill anybody, but it did cause a lot of damage to people's bodies and almost entirely on the face. After watching that video, I imagine you know why. Big old meteorites coming down, big flash of light as it breaks into pieces. People are hanging out in their office or their school. They see a big flash of light outside. They run to the window. Light travels a lot faster than sound, and shock waves travel at pretty much the speed of sound. And so the shock wave arrives quite a bit later, blows out the windows onto people's faces. So if you see a meteorite that big, be careful. Probably the best thing to do is lie flat on your face with your mouth open. I don't know if I do that. I kind of want to see it. At the very least, open your mouth, because that way there can't be a pressure differential in between what's the shock wave passing by you and being around your ears and the pressure inside of your mouth. Because a pressure difference in your mouth in comparison to right outside your ears can rip your tympanic membrane right apart. Oh, so again, we talked about the ecliptic. Notice that all of the planets are in a tight plane. They're all basically orbiting in the same direction. And those are the things in blue. The things in red are all the minor planets, and they do not necessarily follow the ecliptic. But the existence of the ecliptic is the reason that all the planets follow the exact same path that the sun does across the sky. We're all moving around basically as flat as we would be moving if all the planets in the sun were placed on a very flat dinner plate. Go ahead and sketch these because you should know all the minor planets, because then you can impress people at parties. So, one more note about sky motion. If you hover over the North Pole of the Earth and you back off, you'll see that all of the planets, including the minor ones, orbit the sun counterclockwise. And almost every planet spins counterclockwise, with the exception of Venus and Uranus. And those are probably the result of severe collisions in the early solar system. Now, things that orbit in the opposite direction are unstable. If you were orbiting around the sun clockwise, your orbit would decay. You'd eventually plunge into the sun, which is a big part of the reason that pretty much nothing in the solar system orbits around the sun clockwise. And I'm going to stop because we are on to seasons. And that is a separate recording. Everybody have a great day.